So in the directed case, the factors were conditional probability distributions, and then the joint distribution factorizes over these conditional distributions. Now each such factor captured the interaction between the connected nodes. Can we use CPDs in the undirected case? Whenever someone asks this question, the answer is always yes, we can. No, we can't, right? Why? See, CPDs don't make sense in this case because there is no direction. What does a conditional probability distribution mean? It means that something given something. So there is already this asymmetry there, right? You're saying that one random variable go on the given side and the other random variable is going to say on the other side. There is always this asymmetrical relation is there. And the whole point of undirected graphical models or Markov networks is that you don't have this asymmetry. Do you get that? So now what is the factor associated with every node in a Markov network? Probability that they interact. But how do you formally say that? Then are you saying that it should be a joint distribution of A and D? Okay, that makes sense. What did we actually want to capture? Okay, factorization of the joint distribution. And between two nodes, what did we want to capture? Strength of the interaction, right? So we are getting too obsessed with this probability distribution. That's where we are thinking of answers in terms of probability distribution. But always remember that you could always think of real numbers, and then from there getting to a probability distribution is not very hard. Why? Because always you can do normalization, right? So let's start thinking in terms of real numbers. So every edge, let it capture the strength of the interaction between those two nodes. How to go from there to a probability distribution should be straightforward, at least on paper. Do you get that? Do you get the motivation? Because we cannot use conditional distributions, right? Okay. So now we want these factors to capture the affinity between the two random variables. So just as in the directed case, the factors captures the conditional dependence. Here you want to capture the affinity. So it's not very different, right? So there you wanted to capture the conditional dependence between the parameters, and here you are saying I want to capture the affinity between the parameters. So even in the undirected case, we want each such factor to capture the affinity, and we could have factors of the following form, right? We could say that there is one factor for AB, another factor for CD, another factor for BC, and another factor for AB. So what's the difference that you see from the connected case, from the directed case? There the factors were associated with nodes. Here the factors are associated with edges, right? Because edges is what you want to capture, not the nodes. Because if you capture the nodes, then you are introducing some kind of a asymmetry. That's what directed graphical models does, right? So for every edge that you have, and we'll revisit this statement of every edge, okay? So I could have factors of the following form. And what should each factor actually give me? So if I say I want phi 1 of A comma B. Now remember and go back to the discussion that we had about marginals, joints and conditionals. Whenever I say P of A comma B, what do I actually mean? Joint distribution, but what does that mean? I want a value for every value that capital A and capital B can take. So now if I want a factor for A comma B, what does that mean? I should give a value for every possible value that A and B can take, right? Does that make sense? So what I'm asking is, what's the strength of a negative interaction between A and B? That A also has the misconception and B also has the misconception, right? So that's, in fact, we defined it the other way, right? So that's A1, B1. So 1 is for misconception and 0 is for no misconception, right? So for each of these things, I want to give values. So I could give some values. Everyone can focus on this table, right? So I have given you a factor associated with every edge in the graph. And for every factor, I have defined these values, that A0, B0 is 30. And you can just map it back to the conditional distribution. In fact, I can just say that the directed graphical model is a special case of the undirected case, where these factors happen to be the conditional distributions, right? Okay, so we'll come back to that. Let's ignore that for now. But now you have these 4 factors. Yes, so that's okay. I'll come to that. I have it on the slides, right? So that's an interesting question. So he's saying that I want the strength of the interaction, right? So they always interact in the same manner. So A0, B0 is 100, A1, B1 is 100, A1, B0, A0, B1, all is 100. Right? That's the strength of the interaction. What's wrong with that? Think in terms of data, things in terms of past experiences. So we'll come back to that, okay? Who will give us these values? Who will give us these values? It's easy to write values, but who will give us these values? Textbook. We'll have to dash these values. Title of the course, second word from the title of the course. We'll have to learn these values, right? Always, right? I mean, what are factors? What did I say? I'll interchangeably call them parameters, right? So these factors are the parameters of your model. These are things that you will have to learn from data. Now, do you get an intuition for why this would be different? Does that make sense? Okay. Just as the conditional probability distribution, no one is going to give it to you. You'll have to learn it from the data. Similarly, these factors and the values associated with the factors, you'll have to learn from the data. How? How will you learn these from the data? How? So in principle, if you have a lot of past interactions between A and B, then you could learn this from data. Does that make sense? Right? How is still not clear, and that's what we'll do over the next 1 or 2 weeks, right? So that's the purpose, that's the eventual goal that we are heading towards. That if you're given these kind of undirected graphical models, and we'll actually focus on a very specific undirected graphical model from the family of graphical models, and we'll see how to learn these parameters, okay? But you have to understand that these factors are the parameters of your network. So now, just as in the classification case, if I ask you what is probability of this image being an apple, you use all the parameters in your network that you have learned and finally give me that softmax output, which tells me what's the probability of this being a network, right? And you learn those parameters from the data. Now the questions are not very different here. You're asking me the same question, what's the probability that A has a misconception? That's very similar to the question, what's the probability that this image is an apple, right? And just again, as you have parameters there, you'll have parameters here also, right? And you'll have to learn these parameters from some data. How is a big question. There's an entire course on that, so I encourage you to take it next time. But we'll take some parts of it and do whatever is relevant for us, right? So we'll get there. But I want you to understand that this is not free. This will come after a lot of hard work, as you will see in the last assignment. Okay. So roughly speaking, phi 1 AB asserts that it is more likely that A and B to agree, right? So that is what it is asserting, that both of them being 0 or both of them being 1 is more likely than the other case. So now this is based on our past data, right, that we would have seen a lot of interactions between A and B, and they tend to kind of agree with each other or convince each other and are not in this constant state of debate with each other that they say that, okay, this is wrong, this is right, and so on, right? So that's why these factors need to capture these weights, that the strength of the association is more in the positive or the agreement case as compared to the disagreement case. The other thing that this is capturing is that it is more likely that both have the misconception rather, sorry, I forget 0 and 1, but what it says is that 0 was no misconception, right? So it's more likely for both of them to not have the misconception than have the misconception, right? So what that means is that probably A and B are independently capable of resolving their misconception, and given the fact that they often tend to agree, once they have cleared the misconception, they'll pass it on to the other guy, right? So that's why in the end, both of them will not have a misconception. That's what this is saying. A0, B0 is more likely than A1, B1, the case where both of them have a misconception, right? So these are again things which I have just written these numbers, but you have to learn these from the data, right? At least can you imagine that you will be able to learn this from the data? Imagine. Okay, fine. And we could have similar arguments for the other factors. So these other factors are B, C, C, D, D, right? For all these factors, now for every assignment to A and B, we have learned the strength of these associations. Now once I have this, I don't know what I wanted to notice here. Okay, these tables do not represent probability distributions. That should be plain obvious. The values don't lie between 0 to 1, they do not sum to 1, right? And they're just weights which can be interpreted as the relative likelihood of an event, right? We're just saying that it's more likely for A0, B0 to happen than any of the other cases in the table, right? That's what these numbers are actually trying to capture. And this is fine. For the representation of the factors, it's okay if you're not still dealing with probability distributions, but what do we eventually want? We want a probability distribution. And what's the probability distribution that we want? The joint distribution. So now how do I write the joint distribution? How do I write the joint distribution? Yeah, that's fine. How will you write the joint distribution? Can I write it as P of A, B, C, D is equal to phi 1, phi 2, phi 3, phi 4? Can I write it as that? And then what will I have to do? If I normalize this appropriately, would you be fine? I'll include a Z. What would Z be? Summation over all possible assignments for phi 1, phi 2, phi 3, phi 4. Does that make sense? Right? So that's one way of taking a set of real values and converting them to a distribution. And that's what I started with, that don't worry about these values having the properties of a probability distribution. That means they sum to 1 or lie between 0 to 1 and all that. Just give us some values and then we can figure out how to convert them into a probability distribution. And this is one way of converting that. And now your joint distribution would essentially be a product of these factors that you have. Is that fine? Okay. So now once again, our original goal was to take these variables, use a graph to encode the dependencies or independencies between them. Once you have the graph, learn these factors associated with the graph, and then express the joint distribution as a product of these factors. Right? So we have achieved our goal. Is there anything else that we need to do? Are there other cases possible? So let's see, right? So let us build by adding some more variables. Now suppose this is the graph that we have. Now we have more students and these are the interactions, right? So can you tell me can you explain this graph in English to me? What does it mean? For example, what does this mean? The students A, D and E form a study group, right? And it also means that A and E independently also can form a study group. Okay. So in the earlier graph, my factors were these edges. Now, should I have a factor for every edge in this graph also? Again, my quest is the same. I want to now learn a joint distribution over these 6 random variables, and again whether these 6 students have a misconception or not. Right? Now, what should my factors be in this case? I can of course again do the same thing. I can again have factors for every edge and then partition the joint distribution over these factors. Can I do something smarter than that? What can I consider instead of edges? A group. What's a group in graph terminology? What will you take from here? We'll take the dash in the graph, dashes in the graph. What does AED form? Yeah, it's a valid answer. In terms of graph theory, what does it form? A clique. Why is not everyone answering? Why did that brave man have to answer so loudly? Oh, okay. So, okay, what is a clique? Okay. So, if you have, I hope I defined it properly. So, if you have a set of nodes and every node is connected to every other node, then they form a clique, right? So, all the nodes in the set are pairwise connected to each other. So, that's exactly what is happening in a triangle, that all the nodes are connected pairwise, right? So, instead of edges, does it make sense to take cliques? What would that actually mean in terms of number of factors, number of parameters, and so on? Reduce the number of parameters, right? So now you'll have factors associated with the cliques instead of factors associated with the edges, right? So now can you tell me, again this is just a definition of the whole network, which I just explained that these guys form a study group and so on. Now what should the factors be? You could still have these factors, right? I could have a factor associated with every edge, and then I could just normalize that to get a probability distribution, okay? Instead, we could do something smarter. We could have a factor associated with every maximal clique. What do I mean by a maximal clique? So remember that A and E is also a clique, right? Because there are only two nodes and they are connected, so trivially it forms a clique. So when I say a maximal clique, that it's a clique such that I cannot add any more node to it without not making it a clique, right? So AED is a maximal clique, because if I add any other node to it, then there is at least one node in A, E, and D which is not connected to that node. Everyone knows what a maximal clique is? Please raise your hands. Okay, now everyone knows. Fine. So I'm saying that the factors would be maximal cliques. In fact, even in the simple example when we had A, B, C, D, the factors were actually maximal cliques. They were just trivial maximal cliques of size 2. But now I'm saying I'll have maximal cliques of size 3. Everyone is fine with that? Okay, so now my factors are going to be cliques which look like these, right? So remember that I have some cliques of size 3 and some cliques are still of size 2, depending on the nature of the graph. Okay, now what if I add one more student? What would the factors be now? One factor for everyone said ADG, another factor for ABF, another factor for BC, one more factor for CD. So everyone gets this? So we now have maximal cliques again. Now the thing that I wanted you to understand is that I did not choose to take each of these as separate factors, right? There are three-sided cliques inside that one four-sided clique, right? I did not choose to take them independently because I was interested in maximal cliques. Okay, so every maximal clique in the graph, I'm going to make it as a factor. Is that fine? Okay, see right now what we're doing and what we'll continue to do for this discussion is that we're only talking about intuitions. All these intuitions are backed with solid theory, but I don't have the time, neither the scope to cover the theory in this course. I'll give you pointers, you can go back and look at those, but as long as you understand the intuitions, this suffices for this course, right? So why maximal cliques and all that, there is a solid theory behind that, but I won't get into that, okay? So now, remember that for the directed case or the Bayesian network, the distribution factorizes over the conditionals or the local probability distributions. Now in the case of a Markov network, the distribution factorizes over what? It factorizes over some factors where each factor is associated with a maximal clique in the graph. And remember that you could choose, if you want, to not focus on the maximal cliques but take even sub cliques also. But it's that if you make maximal cliques, there is no, see in the case of, that's the distinction that I want you to understand. In the case of Bayesian networks, things were conditional probability distributions, right? So you don't have a choice of whether I can take A given D comma C or A given D or whatever, right? Whatever A depends on, you have to take that as a factor. Here now you have a choice. You could say that I would like to focus on this separately because maybe learning this properly would give me better understanding of the joint distribution, right? Or you could choose to learn the entire clique together because maybe that is more efficient to do or something like that. So you have that choice. Probably the smartest thing to do is to focus on the maximal cliques, but later on I'll also make assumptions where in addition to the maximal cliques, I might also be interested in some of these local factors also. Okay, all that is valid. The only thing that we're doing is in the end we're ensuring that the graph factorizes over these factors, the probability distribution factorizes over these factors, and we add this partition function which is z to make sure that at the end we get a distribution. Even though these factors are not distributions, unlike the Bayesian case, in the Markov network these factors are not distributions, but we can always normalize them by adding the partition function and get back a distribution. Okay. Okay. So I think probably stop here.